Okay, guys. So today is lecture number 5. Okay, of the fundamentals of manufacturing processes. Today we are going to discuss about the design of a gating system and its associated numerical problems. Numerical problems I'm taking for the top gate system that we discussed last time. Okay, so that first we will discuss that one, and then we will move to the next part. Okay, guys. So let's. And one more thing, I just want to brief you that this class is of 2 hours. Okay, so I will try to make it. Little bit not that much boring. Okay. So this is the numerical problems, guys. I want your concentration toward this side. Like I'm expecting the whatever the uh, you will take the numerical problems, okay, very seriously. So whenever I will ask you that, at least answer me. Okay, so this is the numerical problems. Okay, a 200 mm long down sprue. Okay, so this is the pouring basin. Okay, this is the mold cavity. Okay, because top system we are using, top gate we are using, so we discussed last time that this is the gate. Okay, means this is the pouring basin where we are filling the molten material. So here we are filling the molten material. Then this is the top cross sectional area of the sprue. This is the sprue. Okay, okay, and this is a mold cavity. This is the mold cavity. Okay, so okay, let's discuss. This is the 200 mm long down sprue, has a cross section area of 650 mm square, where the pouring basin meets the down sprue. Pouring basin meets the down sprue. It means that this is the pouring basin and this is meeting the down sprue. So here it is exactly not defined the sprue, but it defined by the down sprue. So where it is meeting, the cross sectional area is 650 mm square. So this is at the meeting point. Okay, so this area, cross sectional area, is 650 mm square. Okay, and the length of this is sprue from here to here is 200 mm. Okay, that is at the beginning of the down sprue. Beginning of the down sprue means from here we are filling the molten material. So this is the beginning. Okay, a constant head of the molten material is maintained by pouring basin. Okay, the flow rate, the molten metal flow rate is 6.5 into 10 to the power 5 mm cube per second. So here this is not the mass flow rate, this is the molten flow rate, means volume flow rate, because this is also can be defined by the unit of this, that is a mm cube per second. Okay, so this is the q is given to you. I will write the things first. Just discuss the what is the given, the parameters is given to you. So consider the end of the down sprue to be open to atmosphere and acceleration due to gravity of 10 to the power 4 mm per second. Sorry, yeah, mm per second square. So this area is open to atmosphere. Means here we are just keeping this mold cavity like this, and this area is open to atmosphere. Why it is mentioned? Because in the last time we discussed that whenever like we are talking about the pressure at these point, like this is a 1 point, this is the second point, and this is the third point. So this, whenever we are talking about the pressure at these areas, then we consider the atmospheric pressure, where p1 equals to p2 equals to p3, and that is equals to atmospheric pressure. Fine. Now the acceleration due to gravity, that is g value, is given to you, that is 10 to the power 4 mm per second square. Now if you just consider this value into meter, then it is 10 meter per second square, because 1 meter is equals to 1000 mm. Okay, the area of the down sprue in mm square at it ends. So here basically we, it's asking the what is the cross section area at this place, at the end. Okay, so this is the end portion of this, or exit of this, we can say exit of the molten material. So at this, what will be the cross section area? Okay, avoiding the aspiration effect, because that's why we are using this taper section, so that air aspiration effect, or the porosity when the molding this air has become a part of this mold cavity, so that can be avoided. Okay, so at that time we want this cross section area. So here the four options is given to you. By the way, this question was asked in GATE examination 2007 in mechanicals, but this is a very good problem, that's why I took it. So let's discuss, because very new students are here. So I'm just taking this problem. You just tell me the values that after calculating. Okay. So here what we can do is, here we have to find out at the third position, we have to find out the cross sectional area. Okay. So what options we have? We have till now we have seen only two principles, that is Bernoulli's equation and the continuity equation. Now continuity equation is defined like how much the volume flow rate, that is Q, or volume flow rate we can say, that will be equals to A1 into V1. I am writing just V1 with the velocity small v1, so, and the capital V we will consider as volume. Okay, so this is A1 into V1, that is cross sectional area. This is the cross sectional area at the A1 cross section. Okay, and this is the velocity at that time, that will be equals to A2 into V2, because this is a volume flow rate and it will be constant throughout. That will be equals to V2 into A2 into V2, because this area is increasing, it means the velocity will be sorry, if this area is decreasing, it means the velocity will be increasing in the same proportion. Okay, that will be equals to A3 into V3. So this is the volume flow rate, fine. And we have to consider, because now let's see what we have to find out. We have to find out the area at the end. So this is, can I write this as A3 we have to find out. Okay, so A3 we have to find out, the value of this. Okay, so A3, if I simply use this equation, then A3 will be equals to Q by V3, right? Q by V3, and Q is what? That is a volume flow rate, and that is given to you, that is Q equals to 6.5 into 10 raised to power 5 mm³ per second. That is given to you. Okay, so just calculate the value of V3 and just put over here and get the value of A3. So how we can calculate the value of V3? V3 for this one, here the pouring basin height is not given, but we can calculate the height of the pouring basin. Okay, how we can calculate the height of the pouring basin? That we can apply the Bernoulli's equation, consider this one as a datum level, this one as the datum level. Okay, and then you can apply the Bernoulli's equation over here and just get the value of first V2. Okay, so from here you will get the value of HP height. Okay, let's try this. Okay, so I am applying this Bernoulli's equation between 1 and 2. Okay, so Bernoulli's equation between 1 and 2. Okay, so this is the datum level. Okay, so this Bernoulli's equation will be equals to P1 by rho g plus V1 square by 2g plus H1 equals to P2 by rho g plus V2 square by 2g equals plus H2. Okay, so now let's discuss that P1 equals to P2 equals to P atmospheric, means we are just considering what is the conditions is available, then we will put these value into this equation. Okay, so P1 barabar P2, and that is equals to P atmospheric. Okay, V1, this cross section, the velocity at this cross section at the pouring basin is very small. Okay, then V2, so this is almost negligible, and H1, this is this is the datum level, so this is the height. So this okay, this H1 equals to how much? H1 equals to HP. This is the height of the pouring basin. This is a capital HP. Okay, this height. So this is the HP, and H2. H2 is the, this is the datum level, and from this only we have to calculate the height. So this will be equals to 0. Fine. Just put the value in this equation. So this is, just consider this is the equation number. This is equation number 1. This is equation number 2. Okay, just put this value into equation number 2. So when you will put this value, this will be P atmospheric by rho g plus V1 square, so that you can eliminate this one, that will be equal to 0, plus H1 equals to HP. This is P atmospheric by rho g plus V2 square by 2g plus H2, that is equals to 0. So this is eliminated. Now from here, this HP is equals to V2 square by 2g. So this is equation number 3. But here again, for to calculate the value of HP, we need the value of V2. How we can calculate the value of V2? From equation number 1. This equation is equals to Q equals to A2 into V2. So here we need the value of V2. So do we have the value of A2? Because from here we can equate this Q equals to A2 into V2. And from here we can get the value of V2, that will be equals to Q by A2. So we have the value of Q, and do we have the value of A2? Yes, we have this A2 value, that is 650 mm square. Okay, so we can get the value of V2 from this, and we can put this value into equation number 3. Okay, so just calculate this value. That will be equals to V2 equal to, that is 6.5 into 10 raised to the power 5. We are just here, I'm just calculating that in mm per second only. So this is mm cube per second, and just keeping this in mm square only. So this is 650. V2 will be equals to, that is 6.5 into 10 raised to the power 5 upon 650. Guys, can you tell me the value of V2 from here? 1000. Yes, Moshe, right. Very good. So this is the 1000. What will be the unit? This Q is in mm cube per second. Okay, and this is meter per second. Okay, sorry, this is meters mm square. So this unit will be in mm per second. Okay, so can I convert that into the meter per second? Yes, just 1 mm equals to 10 raised to the power minus 3 meter. So when you will multiply with 10 raised to the power minus 3, this will become 1 meter per second. So this is the velocity. Okay, this is the velocity. Okay, so just you have calculated, now you have the velocity v2. Just put this value over here and get the value of hp. So from here, from equation number 3, hp will be equals to v2 square, that is 1 square upon 2g. Now this is the 2, and this g value here, if you are putting this value in meter per second, then this value should be in meter per second square only. Please keep in mind this one. Okay, but here this value, that is g value, is given to you, that is 10 raised to the power 4 meter per second square. So if you will convert that into meter per sorry, here it's given in mm per second square. So if you will convert that into meter per second square, it will become 10 meter per second square. Okay guys, so this, put this value, that is 2 into 10, and just, can you tell me the value of this one? HP. This is 0.05, right? This is 0.05 meter. Yes, Roman, very good. Mushira. This HP value equals to 0.05 meter. Okay, so this is the value of HP. Now we have calculated this HP value. We have this value, a height of this sprue, that is HS. Okay, so now can we get the value of V3 here? Obviously, we can get the value of V3. Okay, so that's now, what I'm doing is I'm applying the Bernoulli's equation between point 1 and point 3. Okay, so now this is the datum level. 3 point is the datum level. So let's move to the, let's take one more page. So now we are considering this one as a datum level. Okay, so this is HP and this is HS. Okay, from 2 to 3. So let's apply the Bernoulli's equation between 1 and 3. Okay, 1 and 3. So this will, equation will become P1 by rho g plus V1 square by 2g plus H1, that is equals to P3 by rho g plus V3 square by 2g plus H3. Okay, now just let's see what is the values is available. So P1, so P1 equals to P3, that is equals to atmospheric pressure. Okay, this is the condition. Is we consider that this V1 is very smaller than V2. So if you will consider this V1 as comparatively V3, this will become very small. It's smaller than V2. Okay, so this is V1 is very smaller than V3. Okay, so this is V3 and H1. So this is the H1, from this is the datum level. From here, this H1 will be equals to this much. Okay, so this is the H1. So if this is the H1, then that is equals to HP plus HS. Fine. So this is H1 equals to HP plus HS. Fine. H3 will be equals to this is the datum level, and this is the third point, and itself only we are considering this datum level, so that will be equals to 0. Now just put this value into this equation. So this will become P atmospheric by rho g, plus this is eliminated, this is 0. H1 equals to Hp plus Hs equals to P3, that is atmospheric, P atmospheric by rho g, plus V3 square by 2g plus H3, that is equals to 0. So this is eliminated from both the side. Now V3 is equals to root square 2g into Hp plus Hs. Okay. So now Hp is already calculated, that is 0.05 meter. Okay. Hs is 200 mm is given to you. So just convert that value into meter. This value that is also given to you, that is 10 meter per second square. So just put the value and get the value of V3. So from this equation, root square 2 into 10, sorry, 2 into 10, sorry, 2 into 10 into HP, that is 0.05, recently you calculated, and this is 200 mm. So when you will convert that into meter, it will become 0.20. Okay. So guys, can you tell me the value of V3 from here? Very fast. Very good. So V3 is equals to 2.23, right? 2.23. Very good. This is 2.23. This is meter per second. Okay, so this is the unit of that. Okay, so now this is the V3, but this is not the answer. We want the cross-sectional area, means at the area of the down sprue at the end. Okay, so this A3 we want. Now A3, V3 is calculated. So we have this equation again. This is equation number 1. So this Q equals to A3 into V3. So just put the value of Q equals to A3 into V3, and V3 will be equals to, sorry, A3 will be equals to A3 will be equals to Q by V3. Okay, so Q, you have the value of Q3, that is 6.5 into 10 raised to the power 5, but that is in mm cube per second. Okay, so here you calculated this value, that is in meter per second. So just convert that into mm per second. So this is 2.23 into 10 raised to the power 3. So guys, can you tell me the value of A3 from here? That will be in mm square, 291.47. Very good. 291.47. Okay, so that is mm square, Roman 290. Yeah, guys, if you are generally like civil engineering guys, you definitely have to appear in many examinations. So guys, always try to keep the value at the 4 digit. Okay, means after the point up to the 4 digit. Like if you calculated this value, supposed to be calculated this value up to 4 digit, then exact value of this here you will get like 290.7. Okay, this is the exact value. So if you will see the answer, so which option will be correct? Option will be C. Okay, so this is the 290.7. This is the C option. Okay, so this is the simple problem. Okay, because it's lengthy, but it's very simple. Okay, because we are just using two equations, Bernoulli's equations and the continuity equations in terms of volume flow rate. Okay, and we are just calculating the whatever the remaining value or the volume that the problems that has been asked. Okay, so this is the one of the problem. Now let's move to the next one, which is a bottom gate. Okay, so this is the bottom gate, and we are going to design. Now here guys, here in this like there are many things, okay, related with the whenever we are designing there are civil engineering guys, there is a physics, food technology. So whenever like you are designing, always you said that on what basis, what criterias we are taking, what parameters we are taking. If I simply say like from my mechanical point of view, then we are whenever we are designing the machine, we are calculating its dimensions in terms of the diameter, in terms of length, in terms of the cross sectional areas, in term when how much amount of the force is applied on that. But here as we are pouring the molten material, so there is no separate forces required. So designing here, the designing of the gating system means how much, whenever we are using different types of the gate, like top gate, bottom gate, and parting line gate. Okay, so when we are using this one, how much time will be calculated, means how much time required to fill the mold cavity, so that there will be a no turbulence. No turbulence means the mold cavity, the casting will be very good, okay, very smooth and very fine. So for that only we are designing. So what we are calculating, we are calculating the time. In the top gate system also we calculated the time, but it doesn't mean that we are not keeping in mind about the dimensions. Because if you will see the last problem, if you will see this problem here, we have not calculated the time. This complete problem is based on the velocity and the area only. If I say area, it means it involves the diameter as well, because here you calculated the area. No doubt, in other words, it can ask you about the diameter, what will be the diameter, right? Or here, how you are calculating this diameter, by using the velocity. How you are calculating this velocity, by using these heights, okay? Or can I say this length of this sprue, or length of this height of this pouring basin? So whenever we are designing, it means that it's we have to consider the parameters, what parameters is given to us, okay? So here in this casting, when we are talking about the designing of the gating system, it means that we are calculating the time, but it doesn't mean that we are not calculating the cross sectional area or the velocity. We are keeping that mind, keeping in that mind as well, okay? So let's go to calculate, let's try to calculate the time during the bottom gate. Okay, so bottom gate, why we are calling it as a bottom gate? In the last, if you will see, this is yeah, this is the top gate. So here we consider this is the top gate. Okay, so this one here, please come look at here. So this is the top gate. Okay, so that whatever the molten material that is coming from the sprue, okay, that is directly filling into the mold cavity. Guys, here I don't have that one. Yeah, here from I can use, because actually, guys, 2 3 students who joined today, this is basically the actual dimensions or the elements that is required. This is the pouring basin, this is the sprue, this is the choke area or the skim bob, we can say. This is a horizontal passage, which is a runner. After that, we are using this as a gate, and this is the mold cavity. Okay, here we are using the riser as well. So that these are just the elements. Okay, so okay, so this is the, like, when we are talking about the top gate, it means that like here. So okay, let's here only. So here, if we are talking about the top gate, it means that whenever we are dipping the molten material, it is directly reaching to the top. Sorry, bottom side only. Bottom side means it should be like this is the glass, okay, and we are pouring water or any kind of the molten material into that. So this material, this water should be filling in this area only. Means it is going, it is filling this glass only. But this glass can be filled in other way as well. Like, I can connect a pipe, I can just make a hole over here, and I can connect with this pipe, like how we are filling the tanks, or uh, sometimes tanks at the home. So we are using this this we are just making a hollow, this cross section area over here, hollow section, circular section, and we are connecting with the pipe. Now we are filling this pipe, means we are supplying the water into that pipe, and this glass can be filled. Okay, so these are the two ways. So if we are talking about the top gate, simply means we are filling this molten material like this, means we are filling the mold cavity like this, means we are pouring like this, okay, or we can pour like this, okay, because whatever the molten material that is coming out through this sprue or this pipe, that is directly depositing inside the mold cavity, right? This is the mold cavity. Or if we are talking about the bottom gate system, it means that this complete mold cavity is like that, and this is the pipe or the sprue or runner, we can say. So this is the runner, and complete molten material is coming through this pipe, and this is filling like this. Okay, so this is the two difference. Top gate, it means from the top the molten material is coming and it is going towards downside, and from the bottom the molten material is coming from the bottom side and it is moving toward the upside. So this is only the basic difference. Okay guys, just a wait please. So bottom gate. So here this figure is like this, but you have to consider this little bit correction in this figure. Actually, this figure is you should look like this. Okay, this portion is not a part of this. Okay, this bottom, this is black portion is not a part of this. Okay, so this H, this is from this here this is the pouring basin. Okay, this is the pouring basin, and up this is the pouring basin height. After this this is the sprue. Okay, this is the chalk, we can say chalk portion or skim bob, we can say. After that, this is the runner from here up to this runner, and this is the gate. Okay, so this is the we are filling this molten material, and this is coming through the runner, and is this is coming toward this. So first it is like filling like this. Okay, this is the molten material going like this. Okay, so from here we are starting. So this is the total height. So guys, this is not we are considering, so please consider up to this one only. So this is the height, that is hm. Hm means the mold height. Okay, and this is the ht. Ht is the total height, but in terms of pouring basin height and sprue height, you can write that is hp plus hs. Okay, but here now we have to fill the molten material, yeah, molten material into the mold cavity. So is like we are filling this molten material like this. From here we are pouring the molten material over here, and it is reaching like this. So as it is start coming inside this mold cavity, like here we are considering as it will enter into the mold cavity, there we are considering that it is a 0 second, means zero time, but there is no time, just start filling. Okay, and as it will fill this mold cavity, the time will be increasing. Okay, 1 minute, 2 minutes, 3 minutes, 4 minutes, like that. Okay, and it will fill some, it will take some little bit time to fill up to this height. Okay, so this is the height, this is the total height, that is the mold height. Okay, and this cross sectional area here, for the simple calculation, we are considering that this cross sectional area is constant throughout. So when you will see from the top view this mold cavity, so it will be looks like a circular in section. So what kind of the shape we are making? We are making a cylindrical body. Okay, we are making a solid cylinder, we can say. So this is a top section, means cross section of this, that is a cylinder, and of some height, that is hm height. So this diameter or this cross section area you can consider that is am. Okay, so this is the cross section area, and this is the height. So volume of this mold can be calculated, that is am into hm, total volume. This is the total volume. Okay, so but here the important thing is, like, it is not direct, like directly we are filling this molten material with the hm height. Here this molten material is start filling from this gate. This is a gate. Okay, this one is the gate. From the gate only this molten material is coming inside this mold cavity. This is a mold cavity. Okay, so from 0 second the molten material is entered. 1 second it will fill spill. 2 second it will take some time, it will try to fill some height. It will take 2 minutes, 3 minutes, 4 minutes, 5 minutes, something like that, and then this h will be filled. So what I'm saying, what I want to say is, this h, this height of the, as it is moving filling, it is moving, it's increasing with respect to the time. So when there is a 0 second, the height is 0, then time something, that time the hm will be reached. So that is the meaning that I want to say. Okay, so here if you will and what you are filling, you are filling the total volume of this, means you are filling the total volume of this. So if I'm here, I'm what I want to consider is, here I'm just considering that this is a h height, means we are considering the ds, that is a cross sectional area. Okay, that is the ds, that is the cross sectional area, that I'm considering. Okay, and this is the cross sectional area that I'm considering, that is a dh of dh height. So why I am considering this dh height? Because it is varying with respect to the time. Fine. So either what you can do is, two things you have to do here. First of all, you have to write the general equation, that is how much time will be needed to fill this much amount of the volume, that you have to calculate. So what you can do is, you can just consider the datum level, this one, this one as a datum level. Okay, you can consider this one as a datum level, guys. Okay, let me take one more step, that why we are considering this one as a datum level, because we have to apply the Bernoulli's equation. But why we are applying the Bernoulli's equation? Why we are applying? Because we have to calculate the time required to fill this much amount of the volume. So this is the volume, means if I am considering that the specific height of this one, how much time will be required to fill this dh height. Okay, so in dh height, how much volume will be there? This is the cross sectional area, which is constant. So how much volume will be there? That is am into dh. So how much time will be needed to fill this much amount of the volume, that we are calculating. So that will be equals to how, what is the volume flow rate? Volume flow rate from this gate. How much of the volume flow rate? Means volume flow rate will be equals to q, and q will be equals to area into velocity. Okay, so this is just this is the gate, so this is consider this subscript, that is area of the gate into velocity of this gate. Okay, you can consider this one. So this is the volume flow rate, that is ag into vg. But how much time will be required to fill this height, this height? Okay, so that is dt. So if you will see from the dimensions perspective view, then this is the cross section area, that is in mm square, and this is the height, that is in mm, so that will be mm cube. This is the volume flow rate, that is mm cube per second. Okay, and this is the multiply by time, so this second or minute will be cancel out. This total will be in the left hand side will be mm cube only, so right and left hand side will be both satisfied. So this we have to calculate this time required to fill this complete volume. Okay, so that we are calculating, but we, for that we need the value of this velocity. And this velocity is of what? This is the velocity of this gate. Okay, now this gate is at what position? This is the first this is the first, this is the second, which is sprue, and this is the third. Okay, so this gate is at third position at this one. Okay, means in the level of this third, that is the datum level. Okay, so we have to calculate the velocity. So now here, if you want to calculate the velocity, then we are not considering this hs and hp, we are considering the ht, that is equals to hp plus hs, total height from the pouring basin we are considering. Okay, so okay, let's apply the Bernoulli's equation. But this Bernoulli's equation here will be applicable between the point 1 and point 3. Okay, guys. So the Bernoulli's equation between point 1 and 3. So this equation will be equals to P1 by rho g. This is P1 by rho g plus V1 square by 2g plus H1, that will be equals to P2 by rho g plus V2 square by 2g plus H2. Okay, sorry, 3. This is 3. Okay, now just first of all, just put what the value is given to us, which is available to us, that is P1 and P3 is equals to atmospheric pressure. Okay, we are directly comparing this V1 with respect to V3, which is the V1 which has a very large cross sectional area, and V3 which has a very small cross sectional area. It means the velocity at this one point is very smaller than V3. Okay, let's talk about this height, that is H1. H1 is the total height, means from the datum level from this one. So this is equals to HT. That is equals to HT. Okay. Now H3 will be equals to, from here I am considering the datum height, because the gate is at this third position only. But through gate only we are filling this molten material. Please look, please focus, guys, that we are filling this molten material. If we will consider this height is equals to 0, it means that we are regularly filling this position only, means we are not moving beyond this, means we are filling, means we are is the molten material is coming from this gate area, but we are not moving beyond this one. How it can be possible? If the molten material is coming, then definitely it will cover some area or height, we can say. So if we are depositing the molten material, if we are flowing the molten material, no doubt it will fill this mold cavity. So this height cannot be constant. Here in this case, this height cannot be constant. Okay, so here what I have to consider, if we are regularly filling this molten material, it means the height will be changed. So that's why initially I considered this dh height, that is some specific height we are considering. So at what height we are considering, that is equals to h. So we will consider that one, that h3 will be equals to h. So this h can be 0 if there is no material filling, then this h will be, at this position this h will be equals to 0. And if we talk about this maximum value, then this h will be equals to hm. So there is no need to worry, means this height is varying from 0 to hm. Okay, this height is vary from 0 to hm. Okay, so if you are initially considering, then you can consider it 0. If you are finally considering, means up to the when completely the mold cavity is filled, so that time you can consider h3. But we have to calculate the total time. Okay, so for that we have to consider this h. Okay, so just put the value over here. So when you will put this value, this will be p atmospheric by rho g plus v1, that is very very small, so that will be eliminated. H1, that is equals to ht, equals to p2 p3, that is p atmospheric by rho g v3, but here we are defining this v3 by the velocity of the gate, so this vg square, okay, by 2g plus h3, that is equals to h. So this is eliminated. Okay, here you can get the value of vg, that is equals to root square this, because this h will come in this side, so this will become ht minus h. Okay, so this has become 2g into ht minus h. Okay, so this is the velocity. So now this is the equation number 1. This was the equation number 1, and this is equation number 2. So just put this value of v3 over here, v3 value of over here. Okay, so this, now this will be in terms of ht and h. So first put the value, then we'll see. Okay, so here this is dt into ag into vg. So vg will be equals to root square 2g into ht minus h equals to am. This is am into dh. Okay, so like here you can keep these term ag and this is vg value over here. So this will be like in the left hand side only dt will be remaining, in the right hand side it will become like am by ag into 1 by root square 2g. I'm just simplifying this equation. This is dh into root square ht minus h. Okay, so whatever the root square, that I just taken it out. Okay, so this is root square ht minus h. So now here guys, we are taking this, we are filling this mold cavity. So when there is a 0 time, the height is 0. When this time will become like complete, when this height is completely filled, at that time the time will be like we are filling with the bottom gate, so just consider that tb. T is in a subscript, it is uh, b. Okay, so this is the total time will be tb. Okay, from 0 to hm height. So just integrate it, okay, both the side. So when you will take the integrations, so you can calculate at that time the total time. So this time initially there is a 0 time, so at that time the height is also 0. When this completely filled, that is equal to tb, that time it will become, height will become hm. Okay, so in this side it's simply dt, in the left hand side, so just integrate it, so it will become t. So this will become t, and this is from 0 to tb. This will be like 1 by root square 2g into hm by hg. Okay, so now guys, I hope all of you are good in mathematics. Okay, so this is the simple integration, that is root square a minus x. Okay, so when you will integrate it, so this will be like I can simply write this is ht minus h raised to minus 1 by 2 into dh. Okay, so x to the power n, so the integration of x to the power n equals to x to the power n plus 1 upon n plus 1. Okay, so this is root square, so this is root square ht minus h raised to minus 1 by 2 plus 1 upon minus 1 by 2 plus 1. But this is not x, this is a minus x. Okay, so when you will integrate it, means you have to differentiate back, because whatever the term is there you have to differentiate. So this will be like a, that will become 0, and minus x, so that will become 1, minus h, that will become 1 h 1, sorry, that because here the integration with respect to dH. So minus 1 is multiplied. Okay, so this is minus 1 is multiplied. So this value is from 0 to hm. Okay, so now just put the value. So this will be like TB minus 0. So this will become TB. Okay, this is 1 by root square 2g into AM by AG. Okay, this is like minus 1 by 2 plus 1, so this will become 1 by 2. Okay, so this is 2, I'm just writing over here. So this is minus 1. Okay, so first of all just put the value over here. So on behalf of h only we are putting the value. Okay, so first put the value of hm. Okay, so this will like 1 by 2 minus 1 by 2 plus 1, so this will become root square ht minus hm. Okay, and when you will put this bottom value, so this will be like on behalf of this h, so this will become 0. So this is minus root ht, minus root ht. So this is minus side is there in outside, so just multiply it. So this will equation will become like, that is tb will be equals to, like, this is 2 and this is root square 2, so this will become root square 2 by g into am into ag root square, sorry, under root, that is ht minus root square ht minus hm. So this is the equation. This is equation number 3. Okay, but here the important thing is, just a minute. Okay, so this equation is equals to tb equals to root square 2 by g into hm am by ag into root square ht minus root square ht minus hm. So this is the equation. Okay, so it means like ht minus hm. So ht minus hm is like what is the height is there. Okay, total height, and this is the hm, that is the mold height. Okay, so now here two questions can be possible. If the question is like, if this hm, if this hm is like is from this side, in the left hand side here we are keeping these elements, and in the right hand side we are filling the mold cavity. Okay, this one. So what we can do is here like you can increase this height, decrease is already this we have calculated, means this we have discussed. What you can do is, first of all just equate this height. This is the height of ht from the datum level, so we are increasing the height of this. Okay, so we are increasing the height of this. So we are increasing the height means we are increasing the height of the mold cavity. Okay, mold cavity. So this is can be possible, like up to this can be possible, or we can go beyond this as well. So if, like, if we are going beyond this, like if we are going beyond this ht height, if we are just going increasing this hm height greater than ht, then we are just simply pouring the molten material from that. We are just keeping the ladle like this. We are just keeping the ladle like this, and the molten material is coming from that. Means this molten material is coming from this side, right? This coming from this side, and then it is filling. So what will happen when the molten material is filled up to this height? If it will go beyond this, then before coming out from this side, the molten material is coming out, start coming out from this side. Why? Because you are filling this molten material from this side, and here this this cross sectional area is very larger than this one, this gate cross sectional area. So it should, because that whatever the height that you velocity that you are getting here, this velocity is that is vg equals to v3 equals to 2g ht, if we simply consider this consideration. Okay, ht, if we consider this height is 0, but as you are increasing this height, it means that this velocity will not be sustained. This velocity will become 0 when it will reach the molded material, will reach up to this height. Okay, so it will become 0 at that time. So because this cross sectional area is larger than this gate, so the molten material which we are pouring, the molten material, that molten material start coming from this side only. So what we have to do, if we have to, if we have the height of the molding material, mold cavity, which is greater than ht, then what we have to do, we have to pressurize this molten material, whatever the molten material that is coming out from this one, we have to use some kind of cross section area over there, and we have to push it. It means we are applying some kind of external force on the molten material. If we have to go beyond this one, so first condition, so this is first condition, if we have to go HM which is beyond HT, then we have to use the external agency or external force. Okay, to fill the height beyond this HT, we have to use the external force. Now what will happen when second condition, when this HM will be equals to HT? So just in this equation number 3, just put this HM barabar HT, okay, equal to HT. So this is TB will be equals to root square, this is 2 by G, okay, into AM by AG. Okay, this is HT, or like HM I can say, this is HM minus this HT minus HM will be equals to, so both are equal, so this will become 0. Okay, so I'm not writing that value, so this has become root square H1. So now simply so this will be the total time calculated to fill the height, that is HM. Now here I just want to show one of the relationship between the top gate and the bottom gate. That's why I'm just simplifying, to simplify this equation I'm just multiplying by the HM height, and here also root square HM, and also like root square 2 upon root square 2. Okay, so I'm just multiplying and dividing, so it will be cancel out, so there is no need to worry. So when you will multiply this root square 2 root square 2, it will become 2 over there on the top. Okay, AM is already there. Okay, root square HM and root square HM, so this will become HM. Okay, and here if you will see, then this is the AG, and this root square 2 and root square G root square HM, I'm just taking this inside, so this is 2G HM. So this is here HM is equals to HT, because that we have already seen by this equation, because the second condition. Okay, so if you will see this equation, this one, so this you can consider like 2G HT. Okay, so this is what, this is the height, this is the total height, so this is the total velocity at this point. Okay, at this point from the gate, when there is a no flow, okay, when the material molten material is not coming, at that time the velocity is root square VGHT. So this is the velocity of the gate. Okay, so just put it like it will become 2 into AM into HM. So AM into HM, that is the volume of the total mold cavity. So this is Vm, and that will be like Ag into root square 2G HT, and that is the velocity of gate. So simply I'm writing that is 2 into Vm, that is Vm is basically the volume, please consider this is the capital V, and this is Ag into Vg, small vg. Okay, so this is the total time that is calculated by using the bottom gate. Guys, why I am writing this equation, because if you will see this equation, if you will see this equation, that is Vm into upon Am into Ag, then just compare it with the here that you calculated, that we calculated, that is this one. In the top gate we calculated this formula, so this is Tp, the time filled, the time required to fill by using the top gate, that will be equals to Vm upon Ag into this root square 2G HT. So this is Vg. Okay, so this equation is equals to this Vm by Ag into Vg, that is equals to the time required to fill by the top gate. Okay, and this is the same conditions, guys, same height I'm considering here, because there also we considered that is HM, here also we are considering the HM. Okay, that time we considered the cross sectional area, that is AM, here also we are considering the area, cross sectional area, that is AM, and similarly for the gate. So here you can write this equation is equals to the time required to fill the by the top gate. So what is the conclusion, that is TB, means time required to fill the molten mold cavity, same volume of the mold cavity by the bottom gate, that will be equals to time twice of the time required to fill the same amount of the mold cavity by the top gate. So this is the conclusion. Okay, that is the conclusion. Please keep in mind this one. Okay, time required to fill the same amount of the mold cavity by using the bottom gate, that will be equals to twice of the top gate when we are filling the mold, same amount of the mold cavity by using the top gate. Okay, so if like what is the meaning is, like here if you consider that this is the bottom of this, okay, and this is the same kind of height, this is the same height. So if this is the time taken of same volume in bottom side and same volume in the top side, so this will filled by the top gate and this will be filled by the bottom gate. So this is the time taken, that is TP, that is top gate, and this is the time taken, that is TB. So this total time taken to fill such kind of gate, that will be equals to TP plus TB. Okay, or you simply write 2 times of TP, so this is 3 times of TP. So why I'm saying this one, because here we will discuss about the parting gate, that's why. Okay, so guys, if you have any kind of problem, I'm giving you 1 minute, you can ask me. I think okay, guys. So let's move to the third design. Here, in this third and the fourth one, step and the parting gate, we are not designing. Okay, I just forgot what the points is written there. We have to discuss that as well. Okay. So this is the point. There are 3 points that just to consider it on. So if you are using the bottom gate, this gate is provided at the bottom of the mold cavity. Okay, bottom of the mold cavity means at this one. Okay, and this is the mold cavity. This one is the mold cavity, and the bottom of that we are providing. Okay, so this is the return. So the gate is provided at the bottom of the mold cavity. Therefore, the material enters from the bottom to the top and fill the cavity. Okay. The velocity of liquid material is very less, due to which there is no turbulence. Why it is less? Because we are filling the molten material, we are filling the mold cavity from the bottom side. Okay, so as we are filling the molten mold cavity from the bottom side, so this velocity will not be high, because as you are filling this mold cavity, because if you are filling, suppose an example, you are filling this glass by using this bottom gate, then as the material is filling up to specific height, this pressure will also be on whatever the material is coming from this side, right? So whatever the liquid is coming from this side, if it is increasing the height, it means that this pressure is increasing. Okay, so this pressure is on what, whatever the material is coming from this side. Okay, so there is no turbulence. Okay, so that turbulence can be avoided. So maximum times we use this bottom gate only. This is preferred for the non-ferrous material. So guys, in the like there is a last slide for the today's session, that is a gate ratio, gating ratio. Okay, so in this basically we will discuss this one preferred for the means non-ferrous material, and in this top gate also I write one term, that is a for the ferrous material. So this top gate is generally used for the ferrous material, and the non-ferrous material we use the bottom gate. Okay guys, so that I will discuss in the last one. Okay, so this is non-ferrous material means the magnesium and aluminiums, we can say. Okay, so parting gate. So parting gate means okay, so this is the parting gate. So all of you are aware about the parting line. That parting line is what, that is dividing the cope and drag part equally. Means we are using these elements in the gating terminology. It was clear that this is the parting line. This is the parting line. Okay, and the top part of that the casting element is cope. Okay, and the bottom part is a drag. So parting line means which is dividing equally the drag and the cope and the drag, right? So it means parting gate means here this is the parting line we are considering. This is the gate. Okay, this is the gate. Okay, this one is the gate. Now this gate is equally divided into two cross-sectional areas. Means cross-sectional area is same. We are not dividing, but we are just keeping a line between. Okay, so we are keeping this line, this is the parting line here. So if whatever the material, means mold cavity material, which is below to this, below to this height, okay, below to this height means this much amount of the material, we can say, sorry, below to this height, this is the parting line, and below to this height means this much amount of the material that can be filled by this cross section area, only this cross section area, red one, please consider, this is the red one, means this blue amount, blue material is completely filled by the red area, and this you can consider this one, which is a green, okay, this is a green volume, is completely filled by this black one. Okay, this is completely filled by the black one. So like, but what we can do is, this is just an assumption, ideal consider we are considering, but when you will see, like the molten, when you are fill the molten material, this molten material will not think that which is red and which is black, it will come together from the throughout the section area. Okay, so if the molten material is filled up to this height, because obviously it will fill first this material, okay, bottom of the whatever the material that is in the bottom, that will fill first, that one. Okay, so first it will fill up to this it will fill, and then it will fill start this material. Okay, so this is up to this one, we can say like we use the top gate, and from here we are filling by using the bottom gate. But here the top and the bottom gate we are not using separately, but in a same combination we are using this top and the bottom gate. Okay, so how we are defining that, if we are filling bottom to this line, then we, this is filled by the top gate, and whatever the amount which is remaining, that is filled, the volume that is filled by the bottom gate. So this, for this, by this cross section when filled, this volume we are calling it as by filled by the bottom gate. Okay, so this is just like that only. Okay, so if we are considering this much amount of the material, then this is filled by the top gate, so the time calculated during this top gate, that is TP. Okay, and this is the filled by the bottom gate, so the time required to fill this volume, that is TB. So this is total time required to fill this parting by using the parting gate, so this is equals to TP plus TB. Now if you are changing the volume, then obviously this will not be two times of the TP, so that is depends. Okay, so this is the total time, so there is no need to calculate the separate time in this one. Okay, so what is the points is written, that is gate is provided along the parting line. Okay, bottom part of the parting line is filled by the top gate, and the upper part is filled by the bottom gate, that we discussed. Okay, to get the advantage of the top and the bottom gates, such gates are like use, means if you want to use if you want to fill the mold cavity which is higher, of great height, means larger in length, okay, then we can use this one. Because in the last time in the part bottom gate, as I said, that if we want to fill if you want to, whatever the molten material mold cavity that we are filling, if it is of beyond this HT, then we have to use the external agency or external pressure we have to use. So to avoid this external pressure, we can use we can increase this height towards bottom side. So this much amount of the material that can be filled by the top gate, and remaining that can be filled by the top gate. Okay, so that can be managed. Okay, now if this height, if this cross sectional area is small, okay, if this cross sectional area is small, then we can use parting gate, bottom gate, or top gate, that depends. Okay, but if this cross sectional area is increasing, okay, so if this cross sectional area is increasing, which is very large enough, okay, then what we can do is we have to use the multiple gates. Multiple gates means simple, means top and bottom gate only, means combination of the top and bottom gate. So when we are filling this molten material, like this much size of the molten material we have to fill, so what we can do is, we can keep the gate in this side. Okay, we can keep the gate in this side. So if we are if we are is yeah, we are filling the molten material in this side. So this molten material can be, this is the mold cavity that we have to fill. So this is the, is we are filling the molten material in this side, so this molten material can be transferred in this direction, means can be come into the mold cavity through this gate. This is the first, this is the second, and this is the third gate. So and this molten material can be entered into this gate, and it can be entered into from this gate. Okay, so if if we are filling this molten material in this pipe and in this channel, and that is coming through these gates like 1, 2 and the 3. So like if we talk about this third gate, then this is like, if this is a complete mold cavity, then this is in the bottom. Okay, this is in the bottom. So if some amount like if this is this complete cavity of V volume is filled by 3 gates, it means that this some amount of the material is entered from one gate, other come entered from second gate, another can entered from the third gate. So this volume will be equals to V1 plus V2 plus V3. V1 means the volume of mold cavity that is filled by the one gate, used by the one gate, first gate, volume of the mold cavity that is filled by the second gate, volume of the mold cavity that is filled by the third gate. Okay, so that we can calculate. So whatever the volume that is filled by the first gate, it should be treated as a top gate, right? It should be treated as a top gate. And if we are taking it into the center, then the whatever the volume that is filled by the V2, it means that is filled by the parting gate. Okay, because here it's a kind of bottom gate and top gate, both we are using. The amount of V3 that is filled by the bottom gate, it means that is time calculate using the formula that is a bottom gate. So that is a kind of step gates we can use. Okay, also if the we are increasing the this volume of this mold cavity, then what we can do is we can connect this passage at the bottom, at the top. Okay, this is the passage we can connect pouring basin through the pouring basin. Okay, and we can enter, we can connect same kind of things in this side. Okay, so this molten material can be entered from this side as well. Okay, so again this time we have to calculate at the time by using the different gates. Okay, so this is the step gate. So what are the points that is mentioned? To fill the large size mold cavity, one gate is not sufficient. It will take a lot of time. It will take a lot of time. Okay, guys, give me just 1 minute. Guys, sorry for disturbance. So this is the kind of step gate we are used to fill the large size mold cavity, and for that one gate is not sufficient because it will take a lot of time if we use the one gate. Okay, in such gate, more number of gates we have to provide one over the another in like a shape gate steps. So this is the first, the second, third, like that. Okay, due to this arrangement, cavity filled gradually. Obviously, it will fill very gradually. Okay, once if the volume is increasing, then definitely we have to increase the number of gates so that molten material can be filled. Because it's a molten material and it's not like a water; it's a metal. Okay, so if you will take a lot of time to fill the mold cavity, then the material will start, as you are filling the molten material, it will be solidified after some times. Okay, so what we want is, till we are filling the mold cavity, it should not be solidified. It will be solid, it will start solidifying once this complete molten material should be done. Okay, so this is the assumptions that we have to consider. Okay, so this is the types of the gates, these four types of the gate that we have to consider. Okay, guys. So next is the choke area. What is the choke area is? Uh, okay. Okay. So here the choke area is defined by the minimum cross-sectional area. Minimum cross-sectional area in all gating elements. Okay. So if you will see, like here. So here like this gate we are using. Okay, so here this is the minimum cross sectional area in all gating elements. So whatever the gating elements that we are using, which is a pouring basin, sprue, this choke portion, or skim bob, this is the runner, this is the gate we are using. So these are the elements, gating elements. So this is the minimum cross sectional area. So minimum cross sectional area will be this one. So here, by the way, we can say that this is the bottom portion of the sprue. So this is the minimum cross sectional area, we can say. So here we are defining it by the choke area. Okay, so if we have to calculate this choke area in terms of like how much amount of the material we are filling, what is the density of that, then we can use this area of this cross section choke area, that is m. This is rho into t tf, that is ct into rho 2g h. Now what is this? I'm just briefing. This is the cross sectional area that this is the minimum cross sectional area, that is a choke area that we have to calculate. Okay, so m is basically the amount of the mass of the molten material. Okay, the mass of the molten material that we are filling. Okay, this is the density of the molten material that we are taking. If we are taking the aluminium and irons, so that accordingly the density we have to take in time. TF is basically the time required to fill the mold cavity. This is the time required to fill the mold cavity. Okay, CD is nothing but it is the coefficient of discharge. Coefficient of discharge, like we consider in the pipe flow, and maximum civil engineers are aware about that. Coefficient of discharge means like how much amount, how the amount of the material can be, not amount of the material, but uh, how the surface of the pipe, okay, how the surface of the ducts, we can say, that is through which the energy can be lost, okay, or force in terms we can say. Okay, so that can be lost. Okay, the means yeah. So coefficient of discharge, and this is like for different kind of materials, if these by the way, these gating elements are usually made up of the very high strength alloys. So the coefficient of discharge is good for that. Okay, because the smoothness is also we are taking accordingly. So this is the coefficient of discharge, and this is a kind of velocity is the same, that is the velocity of the gate, or the velocity at the cross sectional area of the choke, means the minimum at the minimum cross sectional area. So h is nothing but the height, so that root square 2gs, that is a velocity. Okay, so this is the cross sectional area, the minimum cross sectional area. Okay, so how we can calculate the minimum cross sectional area? By the way, till now we have not discussed this formula, because we were just calculating if it is directly given to us, or if the volume flow rate or the velocity is given to us, so that we can calculate this q equals to a into v, a1 b1 a2 v2 a3 v3. So from that we can calculate this cross sectional area. But if we are calculating this cross sectional area by using this one, so this will give you the minimum cross sectional area, and we call it as a choke area. Okay, so generally it is available at the bottom side of this sprue only. So this is a kind of choke area. This is a simple formula only. Okay, next is the gating ratio. So this is the last topic for today's class. Gating ratio is nothing but the uh, it's a like it's defined ratio is like what the ratio between between two quantities. Okay, but here, so what is root of 2gh? Okay, me sure. Okay, so this is root 2gh basically, but here this root 2gh is nothing but this is the velocity. This is the velocity of molten material at the gate, at the choke area, we can say, at the choke area. Okay, so this is the root square 2g8 is basically the velocity. But if we are talking about the height, then this is the height from the pouring basin. If I am talking about this one as the cross sectional area, then this is the total height, that is ht, that is ht. So this is vc will be equals to root square 2g h, or ht also we can write. So this is the velocity. So root square 2gh is nothing but this is the velocity. Okay, in other terms also you can say like by unit you can define that this is a g, that is meter per second square, and this is in meter. Okay, this is the height, that is in meter or mm we can say. So this will be in meter square per second square. So this is the root square. So root square means power 1 by 2. This is ms square upon s square, means pi 1 by 2. Root square means 1 by 2. So this will be like meter per second. And the, what is the unit of velocity? That is meter per second. So whatever the velocity, this root square 2gf, that is representing the velocity. Okay, and this we calculated in the from the Bernoulli's equation as well. Okay, great. So this gating ratio. So gating ratio is nothing but ratio is simple, like ratio between the two quantities. But here this gating ratio we are defining ratio between the three quantities, three quantities or elements we can say, or these elements are related elements of the gating systems only. So here, if this ratio is between the area of the sprue, means please gating ratio means this is the ratio of area, but three elements. First element is sprue, means area of the sprue, that is as we are representing. Second is basically the area of the runner, that is AR we are representing. And third is basically the area of the gate. Please इसके order को change मत करना guys, because if this ratio is in AS, AR and AG, this is the means order. Okay, आप इसको AS AG AR नहीं कर देना, या फिर उल्टा कुछ भी मत कर देना इसको, ठीक है? This is a wrong. It is the ratio of the areas. First it is a sprue, then it is a runner, then it is a gate. आपको अगर ये याद ना हो ऑर्डर, तो प्लीज आप एक ये वाला फिगर याद रखिएगा. फर्स्ट इसमें क्या आता है आपका स्प्रू, then this is a runner, then it is a gate. So please do not confuse. Okay, order ध्यान रखिएगा. This is a sprue, this is a runner, this is a gate. Okay, so this is the order of that. Now this area, this ratio can be increased in two ways. Two ways means, first this is the two example, this is a three example of first one, and the second these two example. Okay, so this examples, if you will see here, the area of the sprue is 1, means overall average area we are considering, because एक single area तो आप इसमें consider नहीं कर सकते, because this is the sprue started from here and ending at here. So there are number of areas from here to here, because if you will see here, because that is in taper in cross section or parabolic shape. So at every length, at every section, the volume is sorry, the cross sectional area is different. So we are just taking the average cross sectional area only. Okay, so this, if the average cross sectional area is 1 mm square, you can say, if the runner then is there, then the area of the runner is increases, that become 2, and the gate that we are using, that is the area of that gate is increasing again. So what kind of shape will become like this is a pouring basin. This is the pouring basin. Okay, then the ratio is increasing. So this gate, just consider this is the cross section area. So this is the runner. Okay, and again the area of the gate is increasing. So you cannot, like, you cannot make like this. Okay, the area is decreased here. So you have to increase the cross section area. It means this will be like this. Okay, so this is the area of the sprue. This is the cross section area of the runner. This is the cross section area of the gate. Okay, so if this kind of cross section areas of this or geometry we are using, then these kind of the geometry is used for the non pressurized gate. Non pressurized gate or non ferrous material. Non-ferrous material, because it has a very low density, so that it can be filled very easily, so there is no need to push it. Okay, so so this kind of system we are using. Okay, and like here you can see other example as well, like here the area is 1, this is 2, or here you can use the same constant area as well, so there is no issue in that. Okay, but this, either this cross sectional area of this gate should be higher than the runner, or this runner cross sectional area should be higher than the sprue, or equal. Okay, so if, but everything is, it's not like 1:1:1, it's not, it should not be like that. Okay, it should be an increasing order, right? This is here we are using 0.5 mm square. This is 1 and this is 1. So this is three examples are of the non-pressurized gate. But if we are talking about these two examples, then for this the shape will be like this. This is the cross-sectional area just consider. This is the runner, okay, and this is the gate, okay. So here this is the cross-sectional area of the sprue. This is runner and this is gate. So now you can see here the cross section area is larger, it is become lesser, and this become minimum at the gate. So this is 3 mm square, this is 2 mm square, this is 1 mm square. This is just a ratio, okay. You can increase it as well, but in same order. Here you can also equate, but this should become lesser at the end, so that whatever like the high density material that we are depositing, we just have to apply the because for that we need a high velocity, okay, to push them, okay. So that's why we are using this combination, okay, that is as ag and ar and ag. This is applicable for the pressure, we are calling it as a pressurized gate, pressurized gating ratio, or this applicable for the ferrous material. Okay, so in other terms also we can say that top gate, for the top gate I mentioned that that is applicable for the ferrous material. The bottom gate, the bottom gate here is mentioned that bottom gate is applicable for the non-ferrous material, okay, and the top gate is applicable for the this gate we use for the ferrous material. So for the ferrous materials, for the ferrous materials we have to use this gating ratio, okay. And for the non-ferrous, like non-ferrous material, or the, if we are using the top gate, then we have to use this type of the gating ratio. If we are using the bottom gate, then that is applicable for the non-pressurized or non-ferrous material, so we have to use this gating ratio, okay guys. So thank you so much guys. If you have any doubt, you can ask me. Till that I'm just taking your attendance.